All right, let's get started. Welcome everyone to security session 2. This is the last session of this conference, so I hope everybody enjoyed the papers throughout the conference. And just make sure to stick around after this session for the closing remarks and the best paper presentation. My name is Nader, and I'm the session chair for this session. We have four great papers in this session, and then I'm gonna start one by one, and then if you have questions, please feel free to use the chat, and then I'll read the question to the authors, which are also present in this session, and then hopefully they answer the question, and then we can go to the next one and so on. So the first paper is let me find the authors, and yeah, the first paper is from KTH. The first author is Khaled. He's a PhD student at KTH, and he received his bachelor in electrical engineering from the University of Calgary in 2013 and master's from KTH in 2016. His current field of research is hardware security, FPGAs, and reconfigurable computing. So let's get started, and then I'm gonna go and play the video.
Hi, welcome. I am Kalenigo, on attacking Trivium at the bitstream level. This work was performed by myself, Professor Dubrova, and my colleague Mihalis Moraitis. We present a method of using bitstream modification to attack the stream cipher Trivium in order to retrieve the secret key, and in the later half of the presentation, we will present two countermeasures that will mitigate against our own attack. We have dubbed these countermeasures as camouflaging and dummy LUT insertion. Let's start with a quick one-slide background on FPGAs, since it is essential to understanding how this attack works. So FPGAs are essentially reprogrammable digital hardware circuits. They are often used in prototyping or in lower volume manufacturing. I've often heard them being described as a Lego box full of logic gates, allowing you to build and wire up almost any digital circuit you want. Of course, this is only partly true, since once the silicon die has been made, the transistors and the wires cannot be moved around. What FPGAs do instead is that they are actually a massive collection of lookup tables, or LUTs, and switch matrices, and of course other resources that give you this flexibility. The LUTs allow you to program in the truth table of your desired Boolean function, and the switch matrix allows you to propagate the outputs of these LUTs to resources elsewhere on the chip. To program an FPGA, these LUT entries, along with the routing, etc., are stored in a binary file referred to as the configuration bit stream. SRAM-based FPGAs are the most prevalent type and will require this bit stream on power-up in order to initialize all resources as per the user design. They are often stored in an off-chip flash memory, so getting a copy of this bit stream is not that difficult. One thing to note, of course, is that this is all overly simplified. For one thing, it is not trivial to just look into the bitstream and infer the user design netlist, because the order of the LUT entries are obfuscated, as well as the routing tables. The Trivium stream cipher consists of a 288-bit internal shift register with various taps and several clusters of combinational logic to mix the bits in a nonlinear but deterministic fashion. It is loaded with a key and initialization vector and is shifted or spun 4 complete rotations before producing a pseudo-random looking key stream that can then be XORed with your plaintext to produce your ciphertext. So what prevents you from simply taking the key stream output and clicking this machine backwards to derive the initial state and thereby the secret key are these 3 AND gates that provide this nonlinearity. In our attack, we propose to locate these 3 AND gates in the bitstream and modify them to convert the state update function to become linear. In our case, we simply set it to output a constant 0. We then upload the bitstream to the FPGA with the faulty Trivium, capture the key stream, and run the equations backwards to derive the initial state and thus retrieve the secret key. It's not so straightforward as to just peeking into the bit stream and looking for a simple truth table with a vector of 0, 0, 0, 1, because most modern FPGAs have 5 or 6 input LUTs, and this AND gate would almost certainly be merged with other logic. The technology mapper will instead try to fit this design in as few LUTs as possible, so these AND gates will be hidden along with other logic. On the right here, we pulled out the combinational portion of Trivium, and as you can see, it has something like 20-some inputs. Obviously, this wouldn't fit in a single LUT either. So we need to figure out how the synthesis tool carves this up in order to figure out the LUT pattern that we should be looking for in the bit stream. Knowing that an FPGA technology mapper typically traverses in backwards topological order from the output to the input, one just needs to enumerate all possible ways a 6-input LUT can cover a 2-input AND. Working backwards from the output ZT, we can see that these 3 functions on our right here are our prime candidates. Now that we have our 3 candidate functions, we use the find LUT program described in reference number 32 to search the bit stream for the LUT patterns, and through the magic of PowerPoint presentation hindsight, we find each function exactly once, exactly how we suspected. So, with the help of the find LUT algorithm, we have the offset that we need to locate the 3 LUT tables in the bit stream. We can now use a hex editor to update the binary values corresponding to our constant 0 gate and re-upload the bit stream to the FPGA. Once it's uploaded to the FPGA, all we got to do is record this faulty linear Trivium key stream for analysis. The analysis of the key stream and retrieval of the key is mathematically straightforward now and is described in full in the paper. We introduce 2 countermeasures. The first one we call camouflaging, and can be used to fool an attacker that is using a similar LUT pattern matching technique to find their target LUT for modification. This involves populating the unused input table entries to make the LUT appear to implement a different Boolean function to the attacker. But because these unused inputs are statically wired to VCC in the synthesis tool by default, they represent table entries that are never actually looked up and therefore have no effect on the operation of the circuit. Furthermore, this approach also sets traps for the attacker, as other logic, such as the mux in the example on the right, can be made to appear as the target function, enticing the attacker to modify it believing that it contains their target gate. But when this occurs, the original implemented function is broken, the circuit behaves erroneously, and outputs garbage for the attacker to analyze. The second countermeasure we present is to add what we call dummy LUTs. These are false LUT tables that appear legitimate to the attacker, but are actually not connected to the routing matrices. Therefore, they do not undergo switching and do not consume dynamic power. This is especially helpful for protecting small designs because it increases the search space the attacker must explore that would have otherwise have been easily eliminated because the synthesis tool would have just placed all 0 in them as they are not utilized in the design. The algorithm for insertion of these dummy LUTs is described in detail in the paper as well. So, in summary, we have shown you how to use bitstream modification to compromise a cipher, which then outputs a key stream created with a linear updating function. This compromised key stream will then allow one to reverse calculate the initial state and review the secret key. In addition, we propose 2 countermeasures, camouflaging and dummy LUT insertion, that both help to mitigate against such bitstream modification attacks. Everything in this presentation is elaborated on in full details in the conference paper. This concludes our presentation. I believe they have allotted several minutes for questions if there are any. But other than that, thank you so much for your time.
All right, thank you, Kale, for this great presentation. I don't see any questions, so I have some. Can you hear me?
Yes, I can. Can you hear me?
Yeah.
Cool.
Well, yeah. So I have a few questions. One is, so you mentioned the countermeasures. Do you have like how much actually improves the defense? Like, do you have it? Did you also put some numbers like how much the countermeasures actually help? Is it like
Yeah, there
complete?
is an analysis in the paper. It all depends on how large the FPGA is, of course. I mean, the larger the FPGA is and the more unused space you have to insert these dummy LUTs, the larger the search space becomes, of course.
Okay, cool. And then and also like the whole attack premise is that you can search the bit stream, right? Like, what if the bit stream is like encrypted? Can you also like do the same thing?
Well, actually, encryption is generally I guess, the industry default, but it's not as secure as one would hope. There are side channel attacks that can recover the AES key used for bitstream encryption, or as many has heard recently, there's been an prevalence of this unpatchable silicon exploit that's called Starbleed, that allow you to read out the decrypted bitstream without the need to know the actual key. So relying on encryption alone is proven risky.
Okay, so basically, if the bitstream is encrypted, you first need to de-encrypt the bitstream first with another attack, and then apply your method. Is that what you're proposing?
Yeah.
Right? Okay. All right. So I think I don't see any other questions. So thank you so much. And
Thank you, Nader.
we're gonna move to the next one. Okay. Yeah. Bye.
Thank you.
Right, so let me introduce our second speaker and open the video. Give me a second. And all right, so the second paper is from UC Davis, and our presenter is Han. She's a PhD student at the Department of.
Hello everyone, my name is.
Pause this. She's a PhD student at the Department of Computer Engineering and Electrical Engineering at UC Davis. She's working with Dr. Human Humayun. She's a fellow of Young Newton Fellowship in 2018. And her research is on developing machine learning algorithms for effectively detecting microarchitectural attacks. And proposing defenses for lightweight defenses for protecting computer systems from these type of attacks. During her master's degree, she worked on scheduling and tuning the big data application for data centers, where she applied state-of-the-art machine learning algorithms to protect the optimal settings to boost performance and energy efficiency. So with that, let me share my screen and start the presentation.
I'm from the University of California at Davis. Today, I'm going to present our work, FaceGuard, a multi-phase machine learning framework for detection and identification of zero-day microarchitectural side channel attacks. In order to further improve the performance of computer systems, there are lots of components are equipped like cache hierarchy, branch, predictor, failing buffer, and etc. Those components do bring performance boost, but also bring new hardware vulnerabilities. Recent studies shows that a new type of attacks, side channel attacks, can observe victims' behaviors and infer sensitive information like password. And there are lots of computers are influenced. And in order to face the challenge of the security threats, brought by side channel attacks, prior works have proposed a serious machine learning-based detection method, but those work cannot detect unknown attacks. Like in this figure, we can see that there are 3 classification models, but they all show very low detection accuracy for zero-day side channel attacks. Another drawback of this work is that most of those works conduct a binary detection, which can only tell it is under attack or not, but cannot give the exact type of the attack, which might be very useful to propose an effective mitigation strategy. In order to address these 2 challenges, our work proposed phased guard. This is a 2-level side channel attacks detector equipped with zero-day attacks warnings and also side channel attacks identification ability. So the whole framework can be divided into 3 parts: the data connection, which victim, the HPC hardware performance counters like cache misses, L1 hits are monitored under normal cases, which means no attack, and under attack cases. And those traces are further pre-processed by dynamic time warping algorithm in order to calculate the similarities between different traces. And during the first phase 1 detection, the detector tells it is under attack or it is under no attack. This is a binary classification. If it is under attack, then the data will go to the phase 2, which conducts multi-classification and gives the type of the attack. This is our experimental environment. So we are using i5 and it has 4 core. And then we also have 16 HPCs for importance evaluation. The reason we conduct importance evaluation is because the number of HPC can connect simultaneously ranges from 2 to 8 in different hardware platforms. And we evaluate our detector in terms of detection accuracy, F measure, and monitoring overhead. And there are 3 testing scenarios in this work we are using. We have 3 attacks each time. In each case, there are 2 of them are used as no attack, which means they are using in the training data sets. And the rest one, the unknown one, does not exist in the training data set. So we first evaluate the detection accuracy with 16 HPCs with our proposed method and traditional method. We can see that under no attack or under no attack, which are meaning 2 main scenarios conducted in prior works, we can see the detection accuracy are very close between our proposed method and prior works. So when we test with the zero-day attacks data set, we can see the accuracy drops significantly by around 80% across the 4 different classifiers, which means the prior detectors cannot detect zero-day attacks, while our proposed method has the ability. And then we evaluated the number of HPC impact on the detection accuracy of our proposed work. We reduced the number of HPC from 16 to 1 HPC. Similarly, we can also see that for victim under no attack, which is the normal case, and under no attack, when we reduce the number of HPC, the accuracy does not have obvious reduction by only 1 to 2%. Even we reduce the number of HPC to only 1. But when we test with unknown attacks, which is the third figure, we can see that when we reduce the number of HPC to 2, the accuracy for most classifiers drops by over 20%, except the Bayes net. And if we only use 1 HPC, the accuracy is only around 70% for all 4 classifiers. So this indicates that if we want our detector has the ability to detect both 3 conditions, we should use at least 2 HPC. And if we choose 2 HPC, the choice of classifiers should be more careful. So in the following part, we evaluate our results with only 2 HPC. And this part, we evaluate the true positive rate, false positive rate, and F measure. We can see that Bayes net and MLP are delivering the high detection performance results compared to the rest HPCs. And we can see that the Bayes net based as a side channel attacks detector is the best model across all implemented machine learning classifiers and achieving close to 1 F measure with a value. And now we also investigate the ability of identifying side channel attacks. In this table, we can see that all the 3 side channel attacks can be categorized correctly about 99.5%, highlighting the effectiveness of the face guard in identifying the class of occurred side channel attacks in the target system. And this one is the monitoring overhead. We can see that the smaller the monitoring granularity, the higher the performance is. And in our work, we choose 500 microseconds, which only incurring 4% performance overhead. And so to conclude, we propose the face guard to address the 0-day attacks and identification challenges. And the experiment shows that the face guard achieving 98% attack detection accuracy and also about 99% identification accuracy. Compared to prior works, the face guard can significantly identifying 0-day attacks by up to by up to 82% at cost of only full performance overhead for monitoring. That's all my presentation. Thank you.
All right. Is Hanny's here? Are you here?
Yes, I'm here.
All right. All right. Thank you so much for the presentation. And I don't see questions, but I have a few. So first of all, so you on one of the last few slides, you mentioned the overhead, the performance overhead. So what is exactly is this overhead? Is the the time it requires for making the decision, or is it the time for like gathering all the performance counters?
Because this work it monitors the HPC of victim applications, and the performance overhead means the percentage of execution time, the actual execution time incurred because of HPC monitoring.
Okay. And then so how long does it take to actually find, like, to detect that there's an attack? Is it like it takes it real time, or you need some offline time and so on?
In this work, okay. In this work, because we use dynamic time warping, this is takes longer. It might have several hundred milliseconds, but the second part is using some traditional machine learning, so they are not that complex, and their computation complexity is also lower. For an average desktop, it costs around several hundred microseconds.
And then one last question is, so you showed the false positive rate and true positive rate. Did you also try to like change the algorithm such a way that reduce the false positive rate? Because I saw like something around like 20-25% false positive rate. Can you tweak the algorithm somehow that it actually reduced the false positive rate?
False. I think in our final results, the false positive rate is good. That is why we actually experiment on a comprehensive number of classification algorithms, so we can search the most effective one, and also has a lower false positive rate. Thank you.
All right, thank you so much. It was a great paper. All right, so let's move on to the next. The next one is from CMU, and Prashant is gonna present the paper. He's a PhD student at the EC department in CMU. His research interests includes VLSI design, embedded FPGA design, and hardware security. With that, let me sharing my screen and start the presentation.
Welcome to the presentation of the paper XSS Accelerator 8 nanometer for the post-quantum digital signature scheme XMSS. My name is Prashant, and I'm presenting on behalf of our team. Quantum computers can render existing asymmetric cryptographic schemes like RSA vulnerable to quantum computing attacks. To counter this threat, NIST has already started standardizing post-quantum crypto or PQC algorithms that are resistant to quantum computing attacks. As the standardization process moves forward, the performance of PQC algorithms is becoming an increasingly important metric. Prior work on performance evaluation of PQC algorithms focus on either software or FPGA implementations. Very few works evaluate ASIC implementations. Our work focuses on ASIC performance evaluation of a post-quantum digital signature scheme called Extended Merkle's Signature Scheme, or XMSS in short. We present the first 28 nanometer ASIC implementation of the XMSS scheme and compare its performance with an equivalent FPGA implementation. I will quickly introduce the XMSS algorithm before going into the implementation details. XMSS relies on hashes, in this case, SHA-256, to provide security against quantum attacks. On the right, you see the XMSS computation tree. It has three main sections: Merkle tree, L tree, and the Winternitz one-time signature instances, also called Watts instances. A Watts instance, as the name signifies, can be used to sign only one message. In order to enable multiple signatures, XMSS uses a Merkle tree structure to combine multiple Watts instances. A Merkle tree of height h can support up to 2 power h signatures. Next, The Watts instance itself is made up of multiple chains of SHA-256 computations, which are depicted as boxes in the diagram. Each chain takes in a Watts secret key, highlighted in red, and applies the SHA-256 hash function iteratively. The outputs of the Watts chains are the Watts public keys, which are marked in blue. The L tree and the Merkle tree then reduce the Watts public keys into a single XMSS public key, which is the root node of the Merkle tree. This reduction is also performed using SHA-256 hash function. Going forward, we will refer to the Watts instance and the corresponding L tree as the XMSS Leaf instance, as depicted by the dashed blue box. We do this as it is the most used and most compute-intensive portion of the XMSS signature scheme. The XMSS signature scheme consists of three main operations: key generation, signing, and verification. The key generation operation must generate the Watts secret keys and the XMSS public key, which is the root of the Merkle tree. Therefore, the entire tree needs to be computed for this operation. This requires 2 to the power h XMSS leaf computations. For the signing operation, the amount of computation depends on the specific Watts instance and the path to the root node. But the worst case for signing still involves 2 to the power h XMSS leaf computations. For verification operation, only one XMSS leaf computation is needed, but it is still the most compute-intensive portion of this operation. Overall, the XMSS leaf computation is the most used and the most compute-intensive step in the XMSS scheme. Therefore, the XMSS leaf computation is the perfect candidate for hardware acceleration. The figure on the right shows the high-level architecture of the XMSS Leaf Accelerator. The design is organized into 3 modules: SHA-256 XMSS, Watts, and L3. The FSM on the left controls the I/O requests to the accelerator and sequences the Watts and L3 computation. It also controls the access to the memory module highlighted in pink that is used to store the intermediate results. The Watts module highlighted in blue has a key expansion unit. This unit generates the Watts secret keys that are inputs to the chains. The chain unit sequences the computation of the chains and produces the Watts public keys, which are stored in the memory. The L3 module reads the Watts public keys and generates a single 56-bit result, which is the output of the XMSS Leaf module. The SHA-256 XMSS module computes the SHA hash function and is specifically optimized for XMSS computation. Watts and L3 modules send requests to this module when a SHA computation is needed. Moreover, SHA is the most time-consuming portion of the XMSS Leaf computation. Since SHA-256 XMSS is the most time-consuming portion of the XMSS Leaf Accelerator, the performance of this module is critical. Therefore, we implemented a high-performance pipeline version called Leaf Pipe and a regular non-pipeline version called Leaf, and study the trade-offs between the two versions. The SHA data path is in the critical path for both the FPGA and ASIC implementations. To reduce the critical path delay, we pipelined the data path in 4 stages as shown in the figure. Since the SHA computation is iterative, both versions require the same number of clock cycles, and the throughput increase in Leaf Pipe is due to the increased operating frequency. Now, let's look at the implementation of Leaf and Leaf Pipe designs. The die micrograph on the right shows the Leaf and Leaf Pipe accelerators implemented in an industrial 28 nanometer 9-metal CMOS process. The accelerators occupy a total area of around 0.28 mm squared. The logic is synthesized using standard VTH cells, and the memory module is implemented using the foundry-provided single-port SRAM compiler. The chip has 16 IOs dedicated to the XMSS accelerators and uses two-way FIFOs to service the requests to the accelerator. Leaf and leaf pipe accelerators can operate up to 800 megahertz and 1 gigahertz respectively. The layout capture on the right shows the placement of various modules in the leaf accelerators. The leaf pipe accelerator is approximately 1.4 times larger than the leaf accelerator. While the area of the SHA and L3 modules in the leaf pipe accelerator increased by 2x, the area of memory and watts modules did not change. Now let's look at the delay and power comparison. As expected, the leaf pipe accelerator has the lowest delay and achieves the highest operating frequency of approximately 1 gigahertz. While pipelining decreased the SHA-256 data path delay, the frequency of the leaf pipe accelerator is limited by the slow SRAM access delay. At the highest frequency, the leaf pipe accelerator consumes around 2.3 times more power than the leaf accelerator. Leaf pipe design is most suitable for applications that need to maximize performance. But if an application is sensitive to power consumption or area, then leaf design is a good choice. In addition to the ASIC implementation, we implemented the accelerators on the RTX7 FPGA. On the FPGA, leaf pipe design is approximately 1.6 times larger than the leaf design. The leaf pipe design is also 1.7 times faster and consumes 2.4 times more power compared to the leaf design at the highest operating frequency. Since the FPGA is implemented in the same 28 nanometer technology node as the ASIC, we can directly compare the delay and power results. The ASIC leaf and leaf pipe designs are 6 times and 9 times faster than the FPGA designs. They also consume an order of magnitude lower energy compared to the FPGA designs. The leaf pipe accelerator has the best energy delay and area delay metrics in the FPGA implementation, but this is not the case for the ASIC implementation. These results highlight that the architectural decisions like pipelining need to be evaluated independently for ASIC and FPGA implementations. To conclude, we presented the first 28 nanometer ASIC implementation of the XSS Leaf Accelerator. We implemented 2 versions of the accelerator, namely Leaf and Leaf Pipe, and showed that the ASIC implementation is 6 to 9 times faster and consumes an order of magnitude lower energy compared to the FPGA implementation. Our results also showed that architectural decisions must be evaluated separately for the ASIC and FPGA, as there could be significant differences in the delay and energy trade-offs. Thank you. And questions?
All right. So, hi Prashant.
Hello.
Hey, thanks for the presentation. It was a great paper. So a bunch of questions.
Because this week has been a hectic week, and hence.
Wait, sorry.
Welcome to the presentation of the paper ASIC Accelerator in 28 nanometer.
Okay, there you go. So so a bunch of questions about the XMS itself. So did you do any comparison with this specific algorithm with other PQC algorithms to just see which one is, has lower overhead to the accelerator design, and generally, like, how does this specific algorithm stands in the general, range of different PQC algorithms?
NIST recommended a bunch of PQC signature schemes, and we just took the hash-based signature scheme. And there are some studies in software which compare rest of the algorithms, but we have not done that specifically with comparison to other algorithms. We focused on, okay, if you take this signature scheme which is recommended by NIST, then how does it scale across different platforms? And what sort of performance you can get out of it, and what applications might be suitable for it.
All right. And so do you have like any numbers from the other like similar type of works that like how does this like stand among others?
There have been only software results. So we refer to a previous paper on FPGA where we have a similar implementation. But in order to have like a equivalent comparison between FPGA and ASIC, we have implemented the same version in FPGA. So those results from the previous paper are comparable, and we just demonstrate the difference from FPGA to ASIC implementation.
All right. So that we don't have that much time left. So thank you so much. And then perhaps we can talk it offline if you want to continue. Okay. Thank you.
Yeah. Thank you.
Yeah. All right. So let's go to the last paper. The last paper is from Zhijing. And he is let me wait a second. Yeah, he's a PhD student. His research is around embedded systems, and he's from University of Florida. So with that, let me start the last video. And
Welcome.
Yep. Reshare my screen and start the last one.
Hello everyone, welcome to the presentation of our work, Hardware-Assisted Malware Detection Using Explainable Machine Learning. I'm the presenter, Xin Pan, and I'm completing this paper with collaboration with Jennifer Sheldon and Dr. Prabhat Mishra. So let's have a quick overview of our work. We will first have a look at the previous steps in related domain, and we will introduce the proposed method in details, which follows by the experimental evaluation. Finally, we will give a short conclusion. So we are dealing with the task of malware detection using machine learning. Broadly speaking, related works can be categorized into 3 different types. The static method, which is more like a software filter, which can be circumvented by obfuscation techniques. And the second one is the dynamic, that is try to keep track of the runtime behavior. However, it is unable to detect the malware with deviation capabilities. Finally, we will have the hardware-assisted method. It do possess the robust resistance. Unfortunately, all of the 3 mentioned methods, they possess some severe problem. That is, they cannot provide any clue on their results. So it works more like a black box. In our work, we want to maintain the advantage brought by applying hardware components in malware detection. But meanwhile, we prepare to grant the method with the ability to give explanation to its outcomes. So here is our proposed method, which is composed of 4 major steps. And let's go over them one by one. First one is model training, which means we still need to go through a traditional machine learning process to have a well-trained model. The data format in this task is the data collected from the hardware component, the embedded trace buffer, which looks like this. So each row represents the value of some specific registers. The columns represent sequential clock cycles. And this table will be fed into the model as a matrix. Because we are trying to deal with the time sequential data, so the structure of the model is selected as the RNA, which is like this. And the training strategy is the general backpropagation. So next step is the perturbation. So what we do is we want to target some input that we want to explain. We perturb them and feed them into the model. So by the forward pass, we will have some perturbed output. So what do we do with the perturbed input-output pairs? That is the regression and interpolation. So remember, we have the perturbed input and we have the perturbed output, so that we can apply a regression on it. Say we try to fit the polynomial to minimize the least square error. So what we can do is, because it is a polynomial, we can always store the terms with the magnitude of coefficients, so that we can know which component of the input takes the dominant contribution to the output. This scheme may thus not give very deep insight into the internal property of the models, but it can at least provide insight into the features. For example, it indicates that which feature is the dominant factor towards the output of the machine learning model. So to fulfill that, let's look at into the experimental evaluation. We deploy our experiment on 4 datasets, and we report the basic functionality compared with the state-of-the-art method. So as we can see, it provides decent prediction accuracy. And meanwhile, it provides very low false positive rate. And here it comes to the outcome integration. So here's an example. For a given input, our method will give coefficients to each column vector. Remember, each column represents for a specific clock cycle. So the intuition we get from this method is that, see, the fourth column, which is the fourth clock cycle, possess the high-risk coefficient, so that we can say that the malicious behavior is mostly likely to happen in the fourth clock cycle. And that's the clue we can get from the classifier, instead of just like a black box. And that's the benefit we get from the expandable machine learning. With that in mind, we come to a short conclusion. So in this presentation, we have a comprehensive review of previous works on machine learning-based malware detection. And we find out that the key problem is the interpretability. Next, we present our work, which is the first attempt in developing hardware-assisted malware detection using expandable machine learning. And finally, we demonstrate our effectiveness in both the accuracy and the useful interpretation of the detection results. With that in mind, it comes to the end of our presentation. Thank you.
All right, thank you. Thank you so much. We don't have much time left, so I'm not gonna ask more questions. So as I said, please stick around for the final part of the conference, which is the closing remarks and presenting the best paper award. And thank you everyone for joining, and hope you have a great day. Thank you.
Thank you, Nadir. Thank you so much. So I'm gonna stop the recording.